It's not a question it tastes good. It gives me a little electrolyte.
Yeah, that too.
So, was this made out of?
Was it made out of? Okay, oh, here we go. Some more.
Was this made out of? Remember, all measurements made from the normal. An optical disc is put in front of the experimental lamp. Optical disc, experimental lamp. A single slit is mounted on the rectangular opening. Place the semicircular block,
no longer parallel,
on the center of the optical axis. Locate the block with its flat lie on a side exactly on a line between the hash marks. Okay, GIGO, garbage in, garbage out. If that thing is not exactly on the line, exactly between the hash marks, you're getting garbage. All right. The ray must strike exactly the center of the flat side of the semicircular block, right at that vertex. Okay, at a given angle of incidence. Note, using the law of reflection, this may be checked for accuracy since a portion of the beam will be reflected.
So you see,
measure the resulting angle of refraction for each indicated angle of incidence. Using Snell's law, find the value of the index of reflection for the block using each, whatever it says, using each observation. All right.
What's up?
So, the first angle is 0 degrees. That means along the normal. Okay, so what I want to do is I want to go right along that line.
There should be no reflection at all.
Well, if the reflection is going to be back along there. So what I get is an angle of refraction of 0. It doesn't bend. It passes straight through the surface. Okay. And now the next one is 20 degrees. 10, 20. 20 degrees is right there. And I want to strike it right on this. And in the dark, there's not enough of a reflection here to really to show it. All right, 20 degrees. Right at the vertex. All right, so an interesting thing to notice is that this is a radius, constant radius, and so that means that this on the inside, if this is the center, then it's hitting along the tangent, and so there's no bending on this surface. Notice? Okay, so let's go, that's 10, I'm gonna call that, 13.5.
Yeah, it just comes straight out. Wait, explain why that is again?
Well, because it's striking along the normal. The normal, you're going to have a normal will be every radius.
Got it.
Is a normal.
That whatever it hits on there is the normal.
Yeah, so we're not getting any bend from the back surface.
Okay.
All right, 30 degrees. And you can see the challenge because you want to get it on here and right there. And that's not quite right, but like I said, there's some slop. Okay, so that looks like that's right on 20 degrees. 20 degrees. Okay, the next one is 40 degrees. 40 degrees. And I'm going to call that 10, 20, I'm going to call that 25.7. And what I'm doing here is I'm looking at the center of the beam. All right, and then 60 degrees. Let's see, 30, 40, 50, 60 degrees.
And we're back.
By the way, this equipment has been used every year since 1994. Or excuse me, 1997. And I ride herd on those kids. You better not be messing with me. All right, so at 60 degrees incidence, that's 30, I'm going to call it 35 and a half. 35.5 degrees. Okay, and then 80 degrees is, wait a minute. Yeah, 60, 70,
80. Oh.
80 degrees. You know what I'm going to do? I'm going to stop moving this, and I'll start moving this. Okay, now check it out. Before we couldn't see any reflection. Now we can. So now we can check that's 80 degrees here, 80 degrees there. And look at the, it gets fat.
Yeah.
And then it comes to a point right here, and I'm going to call that 30, 40, I'm going to call it 42 and a half. Yeah. 42.5 degrees. And then it says go another 5 degrees. So 5 degrees, 85. And what I'm doing is I'm looking at this and that to make sure I'm at, and now I can barely even see it.
Yeah, so what do you call that there?
But it's right about there. That's 40, 50. I'm going to call that 52 and a half. 52.5 degrees. All right.
Wait, isn't this 30 right here?
Oh, it's 42.5, not 52. Yeah. See, this is why you do it with groups. Wait a minute, 42.5.
I think this one was 41.5.
You're right.
It wasn't 100%. I was
right.
Whew.
Okay. So now it says calculate the angle, take the index of refraction. So for each one. And
so ideally you should get the same number.
Should you? And why should you get the same number?
Well, it's the same thing.
But the thing is, that's a very important point. And
the kids will be like,
kids will not get that.
Yeah.
Okay, so the index of refraction for the refracting material is equal to, hello, is equal to incident material sine angle of incidence over sine angle of refraction. All right, I'm going to do 40 degrees. So the incident material is air. That's 1.0003 sine of 40 degrees over the sine of 25.7.
And that's the 25.7 is what we measured.
Yeah, these are
and the 40 is what they gave us.
Yeah. All right, so 1.3 times the sine of 40 divided by the sine of 25.7. I get 1.48. 1.48. There's no units. 1.48. Now that's very close to 1.50, which is what it is.
Which is plastic, yeah.
And notice we're getting it's made out of the same material as that trapezoidal block. But now our angles, before we had to draw lines to put the protractor on, so there was all kinds of slop in what we did before.
Oh, that's a nice comparison.
Yep. All right. As light passes from air into the plastic block, does it bend toward or away from the normal? Well, it comes in at 30 and goes out at 20. That means it's bending toward the normal, right?
Yeah.
Okay. Choose one of your trials and reverse the path the light took. Place the experimental lamp so the incident beam passes over the point you measured as the angle of refraction. It should enter the curved side of the block and strike the flat side. So
that we want to put the thing, we want to have the light come in this side, right?
Yeah, so let's do, well, we use that 40 degrees.
Again?
We use 25.7, so move it like this. 1025.
No, they both came out.
Yeah, both came out. Come on.
They're so like.
I know it's like, they just don't. There's not a good. So there's 25.7 is right about there, and now I have to hit this right at the vertex. 25.7. at the vertex.
That is hard. Oh, right there, yeah.
And that's right
40.
about 40
Boom.
degrees.
Nailed it.
So there's some symmetry going on here, right?
Yeah.
And we could do that for all of them, and it would go right back in the opposite direction. Also, notice again how the light is traveling straight as it passes through this surface. Now, why is that? It's because it's along the normal, along the radius. It's passing along the radius, so the normal would be tangent to the radius at that point. All right, so now, at this point in the lesson, this point in the unit, we want to reinforce what we've been doing. So this is all reinforcement. Your battery's about dead.
One thing that Rolando said is that it's a energy saving mouse. So when the mouse freezes like that, which it's literally always done, you have to click it twice to wake it up. He said it's like a new battery saving technique.
There it is. All right.
I don't know if you ever heard of that, but
Well, it makes sense.
those are the lies that they're feeding me.
But it's always done that. And see, I've got mouses that don't have that energy saving technique. They have an on-off switch. All right. All angles and optics are measured from the normal. Every time. Don't measure from the surface. Okay? Light shining along the normal is not bent when it passes through a surface. We saw that.
Yep.
We came right along the normal and it went right out along the normal. Okay? When light passes a boundary between two materials, it bends according to Snell's law. And we confirmed that with our calculations. And we could go back, well, in fact, we will at some point, go ahead and do calculations about this. So here's Snell's law, where I is the angle of incidence and R is the refracted. So the thing about this, the index of refraction of the incident material is equal to the sine of the angle of incidence is equal to the index of refraction of the refracting material times the sine of the angle of refraction. So, which way did light bend? Well, it was bending we went from 40 degrees to 25 degrees. It got closer to the normal. These are both measured from normal. So this is incoming, is 40 degrees. The refracted ray is at 25.7 degrees. So it's bending toward the normal. All right.
Toward the normal.
So the refracting material has a bigger incidence of refraction, light bends toward the normal. Air is 1.003, the plastic is 1.50. It's going to bend toward the normal. That's just the way it is. If the incident material is larger, light bends away from the normal. We saw that with a trapezoidal block. When it came out, it bent away from the normal. Question?
What's the matter with Barbie?
What's the matter with Barbie? Okay, first of all, what's the maximum amount light can bend away from the normal?
I know it has to do with the internal reflection or refraction or something.
With Barbie? We'll be sending the light beam through the curved side and out the flat side of the block. Before getting any equipment, calculate what the angle of refraction going from the block to the air for each angle and assuming the index of refraction. So first we have them calculated. Let's calculate one.
Okay.
So it's going to be, we want to have the angle.
I think it's that one right there. Oh no, that was for the incident, I think. What does it want? It wants to calculate
the angle of refraction.
Oh, there it is, right there.
This. So the material is 1.50. This is the index of refraction of the refracting material. But the thing is no.
We want
We're going to switch the refractive material. Now it's going from plastic into air.
Okay.
This is going from air into plastic. So what we're going to have to do is switch these.
Mm-hmm.
And what I do is I instead of just doing it like this,
you'll do it with them. Yeah.
So this is the incident material, which is 1.50. And the refracting material is 1.0003.
And then we change the degree to...
Yeah, let's use 30 degrees.
Okay.
Okay?
Okay.
Now, if we've done this right, because it's going from plastic into air, we should get a
Bigger,
larger number
than 30. Yeah.
So we got shift sign, extra parentheses 1.50, sine of 32 parentheses divided by 1.3. I get 50 degrees.
Boop, boop.
So this should be at 30. It should be 50 degrees. Okay?
Okay, and then it says angle of refraction measured.
So the students would, before we turn them loose, before we give them the equipment, they have to make these calculations. All right, so the first one is 20 degrees. That's going to be right here. And 20 degrees, and that looks pretty good right there. So I've got 30 degrees. Okay, so now let's go to 30 degrees. And I gotta hit it right. And check it out, 50 degrees.
50.
We calculated 50, we got 50.
Bada boom. Oh, sorry, that 30 goes here. Because it's the measured one, right?
Yeah, 30, yeah. Okay, and then 35 degrees is gonna be right here. 35 degrees, and I gotta hit the thing. So that's about 10, remember we're measuring away from the normal. I almost started looking at that because it's easier. 10, 20, 30, 40, 50. That's about 58 and a half. 58.5. The next one is 38 degrees. So we're just gonna go another 3 degrees.
30, 40, 50, 60, 65.
66 or something?
66 and a half.
66.5. Now 41 degrees, we're only taking it 3 at a time, but look how much more bend we're getting. So this is 41 degrees. And it's getting hard to see. I pull the blinds down and make it dark in here when we do this. So this is 80, that's gonna be about 70. And notice how it's hard, it's kind of wide thing here.
Yeah.
It's about 77.
Do you just go in the middle there?
Yeah.
Got it.
So we'll call that 77.
I see, okay.
And then we're gonna go to another 3 degrees. We're gonna go to 44 degrees. And
so do you
I don't get anything.
Yeah.
And the kid, Mr. Lincoln, what's going on? Well, and what happens, let's just, you know, here, we should do this. Let's go up here.
Let's do some of the math.
And let's do the same thing. And this time,
we'll just change the
angle of incidence 44 degrees.
Okay.
So I will use a cheat button on my calculator. Second shift. 44.
Oh, it says quit.
No, it says error domain.
Oh, okay. Oh, because it can't do the math or what? Because it's probably bigger.
Because this will not give us an answer.
Okay, there's no answer.
Mathematically acceptable.
Yeah, gotcha.
Okay, so, and what happens is when they go there, Mr. Boykin, what number 44? What? Say, write down whatever your calculator says.
Yeah.
Right, error domain.
Yeah.
Okay, so error domain, and then they go through and everything's working out. They're getting the right numbers, they're getting the right thing, and then
they stumble upon this beauty.
What happens is we have reflection, but there's no refraction. Okay, now I'm going to see if I can very gently do this. And notice that the reflection will get weaker.
Nice.
And then now there's this. So now here at 41 degrees it comes through, but when I get to 42, and why don't you move over a little so you make some shade. There you go. There you go. And I get to a point where it can't get out of the surface.
Trapped. So what is going on?
Okay. And the question is, what's the matter with Barbie?
Oh.
What's the matter with Barbie?
It's like she's got like a torso coming down, and then her bottom part of her torso is also up there underneath her neck.
Weird, right?
Yeah.
Okay, here's the thing. Here we have Barbie in a fish tank. And the photograph is taken from outside the fish tank below the water. Where's the water level hitting Barbie?
At her neck. Is that right?
Okay, this is the water level at the front of the tank.
Uh-huh.
The water level where Barbie is right here.
Ah.
And what you're seeing is the reflection of the lower part of her torso off the water.
Kind of like when you see like a fish, like I've seen a sea turtle like that, where you see the turtle but you see it above it. You see its reflection above it.
Okay, so now we need to go to the next one right now.
Okay, do it. Bada boom.
Now that I know what it takes to wake it up. Okay, do now Barbie. Okay, in the Barbie lab, we sent light from plastic into air. What angle of incidence would produce an angle of refraction of 90 degrees? So say that this was we were sending the light in like this, and it was bending away from the normal. What's the maximum amount it could bend away from the normal? They'll turn it over like this.
Yeah.
What's the maximum amount? Well, what's the maximum amount it can bend away from the normal?
Wait, where's the light coming from again? Sorry.
The light's coming here.
From here.
And here's the block.
Oh, 45 degrees, right?
No, it can go to 46. It can go more
90.
than that. 90 degrees.
Okay.
So 90 degrees is the maximum. So let's just put this in here. $90 degrees. And second enter. And we'll go here and we'll put, oh wait a minute. We want the angle of incidence. Is this the angle of incidence? Yes, it is.
Yeah. It says we want the angle of refraction.
Okay, what we want is the angle of refraction.
Right,
That's
yeah.
what we're solved for.
Yeah,
so
yeah,
what
okay.
we have to do is we want the angle of refraction, we have to divide by this.
Yeah.
And I'm going to write this out because it's really easy to screw up. So
yeah.
the angle of refraction is going to be angle of index
Incidence.
of refraction, sine of the angle of incidence over the sine of the angle of refraction. No, that's not what.
Oh wait, no, it wants the angle.
No, what we want is sine inverse. We want the angle of
Refraction.
refraction, right?
Yeah.
Okay, sine inverse.
N.
N sub I.
Yep.
Sine theta sub I over
N
sub
yeah.
I.
There we go. That's what we want.
Okay, so that's going to be N sub I is 1.50. 1.50 sine of 90 degrees and 1.3.
What is it? The way that you wrote that, you said what would the what angle of incidence?
We sent like from plastic, that's the incident material, into air. That was refraction.
Yeah, but it wants to know. It says what incident angle would produce that. So we actually want to solve for the angle incidence. I just realized.
All right, so we want to solve. I solved for the.
I know we did.
So this is sine inverse in refracting, sine theta refracting.
Yeah, there we go.
Divided by index of refraction, the incident material.
Mm-hmm.
So this is sine inverse. The refracting material is air. Hello.
There we go.
90 degrees divided by 1.50.
Yeah.
Okay, shift sine 1.3 times the sine of 90 degrees divided by 1.50, and I get 41.8 degrees.
41.8.
41.8 degrees. If you remember, when we got to 41 degrees, we got 77. And if we'd gone another 0.8 of a degree, then the light ray would not have come out of the block. It would have been bent right along the surface.
So this is telling us that if our angle, so the maximum that our refraction could be at that 90 mark.
Yeah, the maximum amount the light could bend is 90 degrees.
90 degrees.
And any more than 90 degrees, it's reflection on the inside. Remember we saw the reflection on the inside?
And that's the angle that it would be reflected on.
Okay. Turtle.
Oh, this is probably why I've seen. I have totally, because I went to Hawaii the year before you showed me this, I think.
Turtle and tonal reflection. Here's a turtle. Okay. The principles of optics is things happen at surfaces. Things happen at the surface. Normal is a line perpendicular to the surface at a point on the surface. Here are all our playas. You got the incident ray, it's incoming, the reflected bounces back from a surface, and the refracted passes through and bends. Here's the law of reflection. The angle of incidence is equal to the angle of reflection. Light bends when it goes from an incident into a refracting material. It happens at the surface. The index of refraction reflects to how much the light bends when going from one medium to another. There's Snell's law that we've been playing with. Which does light bend when it goes from low to high index?
Towards the normal.
Towards the normal. And we relate back, I've already graded and handed. Well, what I do is I just give them credit for doing the lab. And then I hand it back to them, and they can look on that, what's the matter with Barbie? And they can answer the question. Which way does light bend going from high to low in index? Okay, it bends, light comes out of the water or out of the plastic, it bends away. So, and I asked, anybody ever done any gigging frogs? And what they'll have is, some of the Laotian boys will know what I'm talking about. And that is, when the water goes down in the canals, the fish and the stuff are trapped, they go with little spheres, and they say, and if you aim right where you see them, do you hit them? No. That's because of the light. What you're seeing is the light coming from the fish, and it bends away from the normal. And the kids will say, "No, don't kill Nemo." And so, the thing is, you have to aim low. And there's a certain fraction of the boys who've done this, and they're Laotians, and they'll know what we're talking about. Here's this question we asked a moment ago: what's the maximum angle light can bend from the normal? 90 degrees. That refracted ray at 90 degrees goes along the surface, and that's called the critical ray.
The critical
ray. So what we've done here, well, actually, 90 degrees is the critical ray. Is that. Okay. And what we've calculated is this angle. That's the critical angle. This is the critical angle. Now, what does that mean? Well, at 90 degrees, if the beam comes out at 90 degrees, what angle of incidence will produce that? Well, that's what we've done. We've calculated what the angle, and that's called a critical angle, and this is the critical ray.
Okay, that makes sense.
Beyond this angle, the light can't get out of the surface. And this is the next day. And so what you have is that it comes in less than the critical angle, it breaks through the surface. If it's right at the critical angle, it goes along the surface. That's a critical ray. And if it is beyond the critical angle, it can't get out, and that's called total internal reflection.
Okay, that makes sense. Boom.
The angle of incidence produces a refracted critical ray, is called the critical angle, and that's what we've got over there.
The angle of incidence.
Okay. And I do a demonstration with a laser at this point. Still in there?
Laser.
Ah, they're right here. The laser.
Laser. Oh yeah. Oh yeah.
This is called a Heaney laser.
Heaney.
What does Heaney stand for?
Helium neon.
That's right. And it's mildly dangerous. All right, so can you see that beam in there? Should we turn
Let me turn that off.
All right, so what we have here is a plastic that has material in it that reflects the laser light back to you. Okay, if we, let me do this with this hand. If we start going through and we get to a particular angle.
Right there, that's the internal. So that's the
That's total internal reflection.
And right the moment before it is the critical.
It can get out.
Yeah.
Yeah. Okay, and so what happens is it stays inside. Okay, it can't get out. And you can see it's coming out, it comes out the end. Like that. And what you can do is it will go around corners.
Cool.
So it'll go around corners, and because, and this is the principle used for fiber optics. fiber optics, you have a glass where the index of refraction between the glass and the shielding material doesn't let the light out. And so this is how information can be transmitted by modulating the strength of the laser beam. And that's how fiber optics work.
Cool.
And it's...
Is that your receipt for it?
I don't know what that is. No, that's the explanation.
Oh, it kind of looked like your receipt.
All right. So the incident ray greater than the critical angle cannot get through the surface. Can't get through the surface. That results in total internal reflection. And that's what we're seeing here, is there's light reflecting from the turtle, and if you were standing in the water above, you could see the, the turtle. But if you get here, the light radiates in all directions off the turtle. You know, I mean, light is radiating off my hand in all directions. If you were standing over there, you could see my hand because light's reflecting off of it. Okay, some of that light is reflecting off the surface because it's beyond the critical angle and it can't get out of the water. Total internal reflection, total internal physics term. Okay, there's this. If you're in a swimming pool and you swim down to the bottom of the pool and you hold your nose and look up, you'll see a circle of light. There's a circle of light. And you can see the sky in the circle of light. But outside that circle of light, you can't see the sky. What you see is the reflection of the pool, because that's beyond the critical angle. So if you have a, you know, from the center here, you have a certain angle, and beyond that, it can't get out. So here, if it goes along the normal, there's no bending. As you increase the angle, here's 15 degrees, 20 degrees, here's 30 degrees, 42 degrees, so it's bending away from the normal. The farther you get, the farther it bends away from the normal till you get to the critical angle where it goes along the surface.
Boom.